In this video, we're going to continue discussing molecular orbital theory. We've seen previously that s atomic orbitals from two different atoms can combine to form a sigma bonding molecular orbital and a sigma anti-bonding molecular orbital, depending on whether the orbitals meet in phase or out of phase. Well, what happens to atoms when they have electrons in their p orbitals and they react to form a molecule? So, for example, what if we had two nitrogen atoms and they reacted together to form a nitrogen or N2 molecule? As we know, nitrogen has electrons in the 1s, the 2s, and the 2p. So valence electrons, if we just focus on the valence electrons, nitrogen has electrons in the s and the p orbitals. What will happen with these two nitrogen atoms reacted to form a nitrogen molecule? How would the atomic orbitals combine to form molecular orbitals? Well, molecular orbital theory tells us that atomic orbitals that have similar energies will combine together to form molecular orbitals. So in other words, the 1s orbitals, atomic orbitals, would react to form a sigma bonding and sigma antibonding. The 2s, those two would react together to form a sigma bonding and antibonding molecular orbital. And then our 2p orbitals, we have a total of 6. So we would get 3 bonding and 3 antibonding molecular orbitals from our 2p. But the 2p are a little different than the 2s because, as we'll see, they can combine a little differently. So let's take a look at those p orbitals. We know that p orbitals, a set of p orbitals, we have one along the x, y, and z axes. And so if we look at them all together, it would look something like this. If we had two atoms that were combining, here we see the p orbitals from one atom and from another atom. The p orbitals can combine in a head-on manner. So these two that are along the same axes, the x-axis, those can combine in phase and out of phase along the same axes head-on. And we also have two sets of p orbitals that can meet parallel or side by side. So here, this p orbital and this p orbital along the y-axis, they can meet in phase and out of phase to form molecular orbitals. And this set of p orbitals along the z-axis, those can combine in phase and out of phase to form, again, two molecular orbitals. So let's look at these p orbitals, molecular orbitals, in a little more detail. As we said, p atomic orbitals can combine along the same axes, head on, and they would form, when they form head on, they form sigma, representing that they are meeting head on, sigma 2p bonding, and sigma star 2p bonding. And of course, the sigma bonding, they meet in phase. The sigma star 2p, they meet, the star representing they meet out of phase. If they meet in phase, head-on in phase, there is an increase in electron density between the two nuclei along that x-axis. You can see that diagram here. If they meet out of phase, there would be a node or a region where there is no electron density in between the two nuclei. And again, that tends to destabilize the molecule when the electrons are there. Most of the electron density would be on either side of the nuclei. Also, the pi bonding molecular orbitals form from a side to side or parallel overlap of these atomic orbitals, which causes there to be no electron density along the axes, but rather above and below the axes. So looking at this diagram, here we have a set of p orbitals, one from each atom that's combining, and they can be either from the y-axis or from the z-axis. So we'll have whatever we're looking at here times 2. They can meet in phase, parallel or side by side, to form pi 2p bonding. And you can see that, again, the electron density here is in between the two nuclei, either above or below. However, if they meet out of phase, the p orbitals, they form a pi star 2p antibonding, where we have a node in between the two nuclei, and most of our electron density when electrons are in these orbitals is above and to the side of the two nuclei. And again, I just want to stress that What we're looking at here would be multiplied times 2 because we would have two p orbitals meeting along the y and the z axes. So here you can see in this diagram the pi bonding and anti-bonding molecular orbitals and how we denote those. Now that we have hopefully a general idea of what these molecular orbitals look like, how many there are, we want to look at how to draw a molecular orbital energy level diagram for a molecule. So let's start with any molecular orbital diagram. We start with the atomic orbitals to the right and left, and we draw the molecular orbitals in the center. So these would be the atomic orbitals for one atom and the atomic orbitals for the other atom that are combining together. Again, here we're just looking at the valence valence atomic orbitals. So our 2s atomic orbitals can only combine head-on, as we've seen before, to give us a sigma 2s and sigma star 2s. That's if they meet in phase, we get the sigma bonding, sigma star anti-bonding if they meet out of phase. So this would represent the bonding. This one up here up top would represent the anti-bonding. Now, what about these p orbitals? Well, the p orbitals, we said they can meet head-to-head, or they can meet side by side. For many molecules, the lower energy orbitals are formed when they meet side by side. So here we have a pi 2pz and a pi 2py. It doesn't matter which one you write first. And we have two of those in the bonding and two in the anti-bonding. As we said before, that's formed when they meet parallel or side by side. So we get two bonding molecular orbitals and two anti-bonding molecular orbitals. And these are pi because of the direction that they meet. When they meet parallel, we designate them with the pi 2py to pi 2pz. Now, finally, we have those two p orbitals that can meet head-on. When they meet head-on, we designate or denote them as a sigma 2p. If they meet head-on in phase, we get our sigma bonding, which would be lower energy, and we get our sigma anti-bonding, which would be the highest energy. And we have only one set of those because only one set would meet head-to-head. So overall, for many molecules, the energy level diagram would look something like this. So let's practice that, and let's do one. Let's see if we can draw the molecular orbital energy diagram for the N2 molecule. Pause the video and see if you can do it. Okay. So here are the electron configurations for two nitrogen atoms. We're just going to focus on the valence electrons for simplicity's sake. So here is the atomic orbitals for one nitrogen and the other. Let's put the electrons in those. Again, just the valence. We have 2, 3, 4, 5s, and 5 over here. Now our atomic orbitals are going to combine to give us our molecular orbitals, which we draw in the center. And we've shown you where those come from already. Now that we have our molecular orbitals and we know how many and their energies, we can put our electrons. We have 10 total electrons. The Aufbau Principle tells us that we start with the lowest energy molecular orbital, fill it up, go to the next one. Now here we have two orbitals that have the same energy. We say those are degenerate orbitals. We put one in each, one electron in each, before we go and double up. So we've placed 2, 4, 6, 8. We have 2 more to place. And so this would be the electron configuration for the nitrogen molecule, according to molecular orbital theory. Now there is one thing to note. The order of the molecular orbitals, we've just shown you what they are. However, the energies tend to change as we go from left to right across the periodic table. In particular, when we get to, say, B2, C2, N2, those follow the same order that we've just shown you. But for O2 and F2, there is actually a crossover point. And notice here, compare it to over here, compared to here, the sigma 2p is lower energy here, and the sigma 2p is higher energy here compared to the pi 2p's. So there's a crossover point where those two actually flip-flop. Pause the video if you need to and carefully look at this. All the energy levels and molecular orbitals are the same. The only difference is that those two flip-flop for molecules such as O2 and F2. Now, let's take a look at that in a little more detail. Say we were looking at O2 or F2 and we wanted to draw their molecular orbitals. We would start with our two S's. Next would come our two p orbitals. They would combine, and the lower energy here, we would start with the sigma 2p and the sigma star 2p, formed by the head-on overlap of the 2p. Then comes our pi 2p along the y and the z axes, and the pi anti-bonding. So as compared to what we showed you previously for O2 and F2, these two have flip-flopped. So let's show you or let's have you try to draw the energy level diagram for the O2 molecule based on what we've shown you just now. Pause the video and give it a try. So here are our two oxygen atoms and their electron configurations. Here, let's look at the valence electrons. Here are the atomic orbitals for our two oxygen atoms. Let's put our electrons in them. Now we need to draw our molecular orbitals. Our 2s and 2p will combine to form these molecular orbitals. We have a total of 2, 4, 6, 8, 10, 12 total electrons. So we start putting them in the lowest energy molecular orbital first. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So here for O2, we would have a molecular orbital configuration, electron configuration that would look very similar to this. So be sure that you understand how these p orbitals combine to form molecular orbitals, the general shape of these molecular orbitals, and you can draw an energy level diagram for any diatomic molecule for the first or second period.